This is section 4.6, related rates. These are really fun word problems, applications of derivatives. Let's take a look at example 1. A ladder 20 foot long, I should have said a 20-foot long ladder, leans against the wall of a vertical building. If the ladder slides away from the building horizontally at a rate of 2 feet per second, how fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? Okay, let's get a picture over here. Okay, so this is the vertical building. This here is the ground. And then this here is the ladder. Okay. Now, what you're going to find is an extremely important skill is being able to label your diagram with some things that are fixed and some things that are not fixed, meaning they change. So the triangle here that we see, one of the sides is fixed. And I hope that you see that it's the ladder, the hypotenuse, and that's going to be 20. That's fixed. That will never change. As the ladder slides down the building, that ladder will remain at 20 feet. What does change, though, is this horizontal distance, and because it changes, we have to give it a variable name, and we're going to say x here. You can call it anything you want. I'm calling it x because it's sort of along the x-axis, and I'm going to call the height of the ladder's position off the ground, I'm going to call that y, and that will also change, hence the variable. Alright, there are 3 parts to the problem. One is given. The really key feature of related rates is being able to label given information and things you're supposed to find with correct notation. So the given information is that the ladder sliding away horizontally at a rate of 2 feet per second. So something's going to equal 2 feet per second. Notice we have feet per second. That's a rate of change. That's a distance over time. So what we want to label this is dx dt. It says the rate of change in x, the thing we labeled x, with time is going to be 2 feet per second. So we're introducing this variable of time, dx dt. Next, we want to determine what we want to find in the problem. So we want to find in the problem, let me locate it. There it is. How fast is the ladder sliding down the building? So what we want to find in symbolic notation would be the derivative of y, that's the height, with respect to time, dy dt. And we want to find that when, it says when y equals 12 feet. Notice my diagram, I did not label my diagram 12. That 12 is at a moment in time, but it will change, and I know I've said that 1,000 times, but because it changes, we're going to label it with variable names. So next, we need a relationship. Okay, in this relationship, we want to be able to tie the x together with the y with other information, in this case the given 20. So what relationship ties the x to the y to the 20? If you're thinking Pythagorean theorem, you are correct. X squared plus y squared equals 20 squared. That's the hard part of the problem. The easy part now is the calculus. We're going to use implicit differentiation. So what I'm going to do, I have this relationship here, and I'm going to take the derivative of the whole relationship with respect to time. So that means x is going to be a function of time, and y is also going to be a function of time. So we treat x like stuff, and we treat y like stuff. So what is the derivative of x squared? It's going to be 2x times the derivative of x with respect to time, dx dt. There's the chain rule. Plus the derivative of y squared, which is 2y dy dx, equals the derivative of 400, which is 0. So that's the calculus portion. Now what we're going to do is, I draw this little funny camera thing, is take a snapshot in time. I take my cell phone and I take a picture of the ladder sliding down the building. This is going to be 20. At the moment in time, we have over here that the y distance is going to be 12. So I can figure out what the x distance is at that camera shot, snapshot in time. I can probably guess at 16, as we have a 3, 4, 5 triangle. So once we have our snapshot in time, the whole problem is just about done. We have to substitute values into our equation with derivatives. So we have 2. Then the value of x at the snapshot in time we found to be 16. dx dt, we come back to the given, and dx dt is equal to 2. So all I'm doing is substituting, plus 2, and then the value of y at the snapshot is 12, and dy dt is the thing we're supposed to find, equals 0. So the problem is just about done. We just have to solve for dy dt. So dy dt is going to equal negative 16 times 2, because I subtract that and then divide the 12, and then that obviously reduces to negative 8 over 3 feet per second. Now I want to pause for a minute here as I want to explain this negative sign. The reason that it's negative, a lot of people want to say, oh, it's negative because the ladder's sliding down. That is not the case. That is not the reason it's negative. We call the distance y here, and the distance y is actually getting smaller. It's collapsing as the ladder slides down the building. So because y distance is decreasing, that's the reason the answer is negative. So we would say the ladder sliding down the building at a rate of 8/3 feet per second. I prefer the mathematical version with the correct sign. Let's take a look at example 2. A camera, here's my camera, is mounted at a point 3,000 feet from the base of a rocket launching pad. Here's my rocket launching pad. And a rocket is rising vertically at a rate of 880 feet per second when it is 4,000 feet above the pad. How fast must the camera's elevation angle change at that instant to keep the camera aimed at the rocket? Okay, so we have a distance from the camera to the launching pad, and from the rocket to the launching pad, and then we also have a distance from the camera that's fixed on the rocket. Alright, so first thing first, in our diagram we want to determine what is fixed. Hopefully you can see the fixed is the distance here, the 3,000 from the camera to the launching pad. The distance from the pad to the rocket is not fixed. It will change, so we need to give it a variable name. We could call it y, we could call it h. I'm going to call it r for the rocket. Then we got this other distance here from the camera to the rocket, and let's just call that, in this case, d for some distance. Then we also have a theta here, the angle of elevation, because the camera is going to follow the rocket. Now theta is in radians. Alrighty here. So we're ready to do the problem. Given. There will always be a rate that is given. In this case it is 880 feet per second. Can you guess the label on that? If you're thinking dr dt, you are correct. The derivative of rocket with respect to time, the derivative of rocket distance. Alright, and it's positive, not because it's going up, but because the distance that we called r is increasing. Next, what do we want to find? We want to find the rate of change of the angle. So, man, I wish I could ask you to do this on your own, but maybe try it on your own. But we're looking for d theta dt, the rate of change in theta with time when the rocket is 4,000 feet above the ground. This rate up here is also when r equals 4,000. All right, next, our relationship. There we go. And we need to relate the r to the theta to the given if we can. So look at your triangle. How can you relate the theta to the r to the 3,000? So hopefully you see tangent of theta equals r over 3,000. Opposite over adjacent. Next step is to find the derivative of the relationship with time. So we have the tangent of theta equals r over 3,000. So this is going to be secant squared theta, d theta dt, the chain rule. Theta is a function of time, and also r is a function of time. So now we have 1 over 3,000 times the derivative of r with respect to t, which is dr dt. All right, that's our derivative equation. Now we're ready to do a snapshot in time. All right, so let's see my snapshot in time. This is always 3,000, so that's good. At my snapshot, this is 4,000. And again, we have a 3, 4, 5 triangle. I wish I could get this into everybody's head, but the key here is don't try to find what theta is at the snapshot in time. You'll go bonkers and have a really ugly equation. What you do want to do is figure out what not theta is, but what the secant of theta is. Let's look at some relationships. Cosine of theta is an easy one. The cosine of theta is adjacent over hypotenuse, so that's going to be 3,000 over 5,000, or simply 3 over 5. So then I can determine what the secant of theta is, and the secant of theta is going to be 5 over 3. That is ultimately what gets substituted in our snapshot in time. So the secant is 5/3. That's going to be squared. D theta dt is the thing we're supposed to find. 1 over 3,000. And then dr dt was given at 880. Like that. So a little simple algebra. We have 880 over 3,000. Excuse me. We're going to multiply that by a reciprocal. See, I want to get rid of this quantity here. So I multiply the reciprocal. So I'm going to multiply by 9 over 25. Let's just call that done. So I didn't simplify my answer. But the units on this, it's really important that you note that this is going to be radians per second and not degrees per second. If you were asked to find it in degrees per second, you would first find it with radians per second. Then you would convert. But I'm a big fan of the radians. In calculus, we use the radians. So our final answer, radians per second. Example number 5. Actually, in your notes, I've changed this to be example number 3. There we go. Okay, so here we go. This is based on a real scenario, by the way, students I used to have. So we have this kid, Walter, and he's running towards the soccer ball, south, down. And we got another kid, Kevin, who's running away from the soccer ball towards the goal, which makes this right triangle as you see here. All right, so we have some given information here, and let's start off with that given information. Let's see. Perhaps we should actually label this triangle first. Let's label this side here W, the Walter side, and we'll label this side of the triangle K. And let's label the distance between Walter and Kevin as D. And then we have an angle theta, which will come in the problem later. Okay, so what's our given information? we'll write given here. Given information. Walter approaches the soccer ball due south at a rate. So that's going to be dw dt equals, now this is going to be negative 12 feet per second. The reason that it's negative is, see, Walter here, his distance is actually collapsing. He's running towards the soccer ball, and you can think of the soccer ball as the origin, and that distance between Walter and the origin is getting smaller, so we say negative 12 feet per second. And then the other given information is that dk dt is going to equal, he's running east at positive 10 feet per second. See, Kevin here is running away from the ball, so that distance is actually increasing. So that's our given information. Now we have two things to solve for here. In part A, what is the change in rate of the distance between the boys? So what I want to do there is find d dt, the derivative of distance with time, the rate of change in distance with respect to time. So that's what we want to do in part A. If I come down to part B, let me move that up, I want to find the rate of change in the angle. So I want to find d theta dt. For each one of these, let's look at the relationship now. Relationship. Now it's above, you have it in front of you, but I've got to scroll up there. My relationship that ties together Walter with Kevin with distance is obviously, again, Pythagorean theorem. W squared plus k squared equals d squared. Let's look at the relationship at the bottom. We want to tie together Walter with Kevin with the theta. So you can see here again we have that the tangent of theta is equal to, now let me look at it here, the tangent of theta is going to be Walter over Kevin. So Walter over Kevin. There it is. I think this is a good opportunity for you to press pause, go through and see if you can answer each one of these, and then unpause to see the solution. Okay, so let's do the solution to A. Let me scroll up a little bit more so I can see my given information. So I have my relationship, and I'm going to do the derivative with time. So we have 2w dw dt plus 2k dk dt equals 2d dt. Now it's okay that I had three variables here because I have two given information. Alright, now I'm going to look at a snapshot in time. When Walter is 6 and Kevin is 8, or let's see, what does that say? When Walter is 6 and Kevin is 8. Yes, that's right. So at a snapshot in time, Walter is going to be 6, Kevin is going to be 8. Again, we'll have a 3, 4, 5 triangle. So this distance here is going to be 10 at the snapshot in time. So I've got to plug everything in. I got 2 times Walter. Oops, Walter is here. Walter is 6 times dw dt, which we found to be negative 12, plus 2 times Kevin. Now Kevin is the 8, and dk dt is 10, which equals 2, and then our distance at the snapshot in time is 10, and we're trying to solve for dd dt. My first move looks like, let's get rid of each of these 2's and then simplify from there, and then dd dt equals 4/5 feet per second after we simplify. Let's go look at the next one. This is again when Walter equals 6 and Kevin equals 8. So we're going to find the derivative now. So we have the secant squared of theta, d theta dt. Ooh, this is cool. We have to use the quotient rule. So bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. And I'm going to come over to a snapshot. 6, 8, 10 theta. And I can say that the cosine of theta is 8 over 10 or 4 over 5, which makes the secant of theta, remember we're solving for secant of theta, we're not solving for theta itself, 5 over 4. So let's plug a bunch of this stuff in. 5 over 4 squared, that's my secant squared. We're solving for d theta dt, and that equals Kevin, 8, times Walter's rate, which was -12, minus Walter, which is 6, times Kevin's rate, which is 10, all over Kevin's distance, which is 8 quantity squared. Now you do the arithmetic. So d theta dt is going to come out to be -39 over 25. And remember the units on this, radians per second.